Every day around us, machines like cars, trains, airplanes, and even power plants are converting heat into useful work. Like car engines burn fuel to create hot gases that push pistons, turning chemical energy into motion. Power plant turbines use steam from boiling water to spin blades, converting thermal energy into electricity. Both are heat engines, taking in heat and producing useful work. But you know what? No matter how perfectly they are built, they can never convert all the heat energy into work. Some of it always escapes as waste energy. And this simple fact is what makes the study of the Carnot cycle so fascinating, because it reveals the ultimate rule that limits every engine in the universe. The Carnot cycle is a beautiful thought experiment designed by a scientist named Carnot to tell us what is the maximum efficiency any engine can ever have. Before we dive into the Carnot cycle, it's important to understand the difference between reversible and irreversible processes. A reversible process is like an ideal, perfectly smooth operation. It happens so slowly and carefully that at every step, the system and surroundings stay in complete balance, with no friction, no heat loss, and no wasted effort. In real life, though, almost everything we see is irreversible. Cars have friction, gases rush quickly, heat leaks, and once it happens, you can't simply reverse it, which means you cannot bring the system and surroundings back exactly to their original state. What is gone is gone. The Carnot cycle is built on the idea of all processes being perfectly reversible, which is why it represents the absolute best-case scenario for any heat engine. Picture this. We have a cylinder with a piston that can move up and down. Inside it, there is a gas, which we will treat as our working fluid. This gas is assumed to be an ideal diatomic gas, which is a fancier way of saying that the gas follows two important relations, PV equals nRT, and PV raised to gamma is constant, where gamma equals 1.4 for this case. Here P is the pressure of the gas, V is the volume of the gas, and T is the temperature of the gas. Consider both N and R as constant for now. Next, this part of the cylinder is in contact with a heat reservoir or an energy source like fire, giving heat to the gas. We label the temperature of the gas as T sub H. The Carnot cycle is made of 4 steps. Let's go one by one. The first step is called an isothermal expansion. Isothermal means the temperature of the gas is constant, and expansion means the gas is simply expanding. In this step, heat flows into the gas from the hot reservoir. Since the temperature is kept constant at TH, and since the process is reversible, the internal energy of the gas does not increase, which means that the gas does not keep any of the heat with it. Instead, all the heat it receives is directly used to push the piston outward. So the gas expands smoothly while performing work on the piston. Also note that in this hypothetical scenario, there is no friction between cylinder and the piston. Now, we will track this process on the pressure volume or PV diagram. Look here, if in an isothermal process T is constant, and these two are constant as well, then P times V is constant. So if this is point 1 with pressure P1, volume V1, and temperature TH, then along the process, as the volume increases step by step from V1 to a larger value V2, the pressure must decrease from P1 to a smaller value P2 in such a way that the product of pressure and volume always stays the same and temperature is still TH. This is why on a pressure-volume graph, the isothermal process appears as a smooth downward curve, much like the graph of y equals 1 over x. The second step is called an adiabatic expansion. Adiabatic means no heat is allowed to enter or leave the gas. It is as if the heat reservoir has been completely switched off. In this step, the gas is completely insulated, so it cannot receive any heat from outside or release any heat to the cold side, but the piston is still moving outward, so the gas has to use its own stored internal energy to do the work. As a result, the energy of the gas decreases and its temperature falls from TH down to T sub C. Now, let us track this process on the PV diagram. You know what? For an adiabatic process, the relation between pressure and volume is given by this rule which I have mentioned earlier. So we get this relation between pressure and volume at point 2 and point 3. This means that as the volume increases step by step from V2 to a larger value V3, the pressure must decrease more quickly than in the isothermal case, dropping from P2 to a smaller value P3 with temperature Tc. Both slope downward as volume increases, but the adiabatic one bends more sharply because the gas is cooling as well while it expands. The third step is called isothermal compression. Isothermal again means the temperature of the gas remains constant, and compression means the piston is being pushed inward, reducing the volume of the gas or compressing it. In this step, the gas is now kept in contact with the cold reservoir, like an ice, at temperature Tc. As the piston moves inward, the gas is being compressed and work is being done on the gas. Since the temperature must stay constant at Tc, the gas cannot store this work as its internal energy. Instead, it releases an equal amount of energy as heat to the cold reservoir, keeping nothing with it. Now, let us see what this looks like on the pressure-volume graph. For isothermal processes, the rule is that P times V is constant. So, as the volume decreases step by step from V3 to a smaller value V4, the pressure rises from P3 to a larger value P4 in such a way that the product of pressure and volume stays the same. So, on the PV graph, this process again appears as a smooth curve like y equals 1 over x, but this time moving inward and upward as the gas is compressed. The temperature of this point is the same Tc. Note that the compression happens because of some external force acting on the piston, which does work on it. The fourth and final step is called adiabatic compression. Now I think you know the meaning of both the words. In this step, the gas is completely insulated from both hot and cold reservoirs. As the piston moves in further, work is done on the gas. Since no heat can escape to the outside, all of this work increases the internal energy of the gas, which makes its temperature rise from Tc back up to Th. Great! For an adiabatic process, this is the rule we follow. When this step completes, the gas returns exactly to its starting condition at pressure P1 and temperature Th. The Carnot cycle is now closed, and the system is ready to repeat the same 4 processes again and again. Awesome! Now at last, we will talk about the efficiency of this Carnot cycle. In the first step, the gas absorbs some heat, which we will call QH, from the hot reservoir, and later releases some heat QC to the cold reservoir, right? Not all of the absorbed heat can be turned into useful work, because some part must always flow out to the colder side. This means that the useful work done in one complete cycle, in moving the piston in and out, is simply the difference, QH minus QC. Now, when we talk about efficiency, what we really mean is, out of the total heat you put in, how much actually comes out as useful work. To calculate this, we take the useful work, which is QH minus QC, and divide it by the total input heat, QH. This gives us efficiency equals this. Now, Carnot showed something elegant about reversible cycles. For a reversible heat engine, QH divided by TH equals QC divided by Tc. When you substitute that into the efficiency expression, you get the famous result for efficiency, which equals 1 minus Tc divided by Th. Remember that Th and Tc must be measured on an absolute temperature scale, or Kelvin. Otherwise, the relation does not hold. The power of this result is that the Carnot efficiency depends only on the two temperatures and not on the gas or machine details. So it is the absolute upper limit any heat engine between those two temperatures can ever reach. To improve efficiency, you must raise TH or lower TC. But practical limits, like material strength, friction, heat leaks, and other irreversibilities always keep real engines below the Carnot bound. Now try to solve this question on your own, and let me know your answer in the comments. If you enjoyed this video, please don't forget to like, share, and subscribe to our channel.